Okay, finding limits algebraically. That means don't use the table in your calculator. Go back to using algebra. So the first thing we always want to do is start by just using direct substitution. Well, if I use direct substitution on top, I'm going to get 1/5 minus 1/5, which is 0 over 0. We've done problems where we've had to factor, but this one, it's not really a factoring problem, but what do you think we could do to manipulate this? Good. Find a common denominator. And this is where you're going to hate me because you have to rewrite the limit as x approaches 0. The common denominator for the numerator, that sounds crazy, but the common denominator for the numerator would be 5 times 5 plus x. So I'm going to need to multiply the first fraction by 5 and the second fraction by 5 plus x. And because there's a minus sign in front of that 5 plus x, make sure you distribute it. So on top, we're going to have 5 minus x. And then divided by 5 plus x. And then instead of dividing by that x that's on the very, very bottom there, what could I multiply by? 1 over x, right? And 5 minus 5 cancels as 0. And negative x over x cancels as negative 1. So I really just have negative 1 over 5 times 5 plus x. And now when I plug in a 0 for x, I get negative 1 over 25. Feel free to show more steps if you, like when you're canceling, if you want to rewrite that more often, you're more than welcome to. But that's pretty much the bare minimum amount of work that I want to see. What do you think we need to do on number 20? Good. Multiply by the conjugate. The part that's kind of giving us the trouble is that square root, so we want to multiply by the conjugate of that numerator. And the conjugate of the numerator is the square root of x plus 1 plus 1. And we're going to multiply that on top and on bottom. This is called multiplying by a clever form of 1. Root x plus 1 over itself really is just 1. Okay, now here's the trick. On top, the part that's the conjugate, I want to FOIL that part out. So I'm going to have the limit as x approaches 0. When I multiply root x plus 1 times root x plus 1, I get x plus 1. The whole point of a conjugate is that the inside and the outside terms cancel. So that's nice. And then when I multiply the outside terms together, I get minus 1. Don't distribute the bottom part. You can't, I mean, if you do it, it's not going to, you're not going to get the problem wrong, but you're basically going to have to factor it back out again. Because on top, the 1 minus 1s cancel, and then we have an x over x. So those cancel. And I just have a 1 on top. So if you were to distribute that x on the bottom, it'd be harder to see that it cancels with that x on top, I think. Okay, so now when I plug in the 0 for x, I have 1 over the square root of 1 plus 1, which is 1 over 2. Okay, sometimes you're going to have more than one variable in your problem. On 21, we're taking the limit as y approaches 0. So the x in the problem is just going to stay in x. What do you think the limit as y approaches 0 is going to be? Exactly, 2x minus 7. See how intuitive calculus is? So it just turns out that this limit happens to have a variable in the problem.
Okay, section 1.4 is about continuity and one-sided limits. And we're going to talk about the one-sided limits first. Normally, when you look at the limit notation, you just see x, or up until this point, you've seen limit as x approaches and then just some number right here. Well, if there's a little minus sign or a little plus sign, then that's a designation that we want the limit either from the left, if there's a minus sign, or from the right side, if there's a plus sign. sign. So the limit as x approaches c from the left is denoted by c minus, and from the right, c plus. Now, the limit as x approaches c of f of x equals L if and only if, that means IFF means if and only if, it's not a typo, if and only if the limit as x approaches c from the left side is L and the limit as x approaches c from the right side is also L. So in order for the limit to exist, the limits from the left and the right have to be equal. And we've touched on that, but we just haven't put it into a formal definition. All right, so we're going to use this graph to find each limit. So the limit as x approaches -2 from the right side. Here's where x equals -2. So, but if I'm coming from the right side, I need to take my pencil and move from the right to -2. Then the y value that this function is approaching is -3. Limit as x approaches -2 from the left. So here's where x is -2. If I'm coming from the left of -2, then the y values are approaching 2. And remember that the value of the function, which happens to be the value of the function at x equals -2, which happens to be 1, has no bearing on this limit right here. It's the y values that you're approaching as you're getting closer and closer to -2, either from the right or from the left. So the limit as x approaches -2 of g of x does not exist. And the reason that it does not exist is because the left limit and the right limit do not equal each other. All right, the limit as x approaches 6 from the right. So here's where x equals 6. If I come from the right, those y values are approaching 4. All right, pause the video and do E, F, G, and H on your own, and when you're finished, turn it back on and check your answers. Okay, on part F right here, I wrote infinity, but truly this limit does not exist, but designating that the y values are approaching infinity is just being more specific and stating why it does not exist. So infinity or does not exist are both acceptable answers to this. I would actually prefer that you use infinity, but you would, if this was a multiple choice question, you would never see an answer choice as infinity and another answer choice being does not exist. But I'd like for you to stick with infinity, but do remember that that limit does not exist. All right, moving on to continuity. For a function to be continuous at a point x equals a, the following 3 conditions must be met. F of a must exist, so the function is defined at the point x equals a. The limit as x equals a of f of x exists, and what we just learned, we know that therefore the left and the right limits have to be equal. And then the third condition is that the limit as x approaches a of f of x equals f of a. And basically in layman's terms, what this means is that the value of the limit equals the value of the function. And anytime you see anything about continuity, you're going to have to, on your paper, discuss these 3 points right here. All right, well, to start off, what I want to do is kind of go through these 3 conditions and give you a counterexample for each condition. So for each of these 3 conditions up here for continuity, we're going to go through and do a counterexample. So I'm going to draw a picture of what would make that not true. All right, so the first condition of continuity is that f of c is defined. So here's an example of when f of c is not defined. And you could just have a big old hole in your graph where x equals c, and f of c is not defined. Another example where f of c is not defined is if, say, you had an asymptote at x equals c. So in both of those pictures, f of c is not defined. All right, number 2, the second condition is that the limit as x approaches c of f of x exists. All right, well, here's a situation where the limit as x approaches c of f of x does not exist. All right, because the limit coming to c from the left side is not the same as the limit coming from the right side, the limit as x approaches c does not exist. And usually the reason that the limit does not exist is the limit as x approaches c from the left does not equal the limit as x approaches c from the right. All right, and then the third condition is that the limit as x approaches c of f of x equals f of c. And remember that that just means that the value of the limit equals the value of the function. All right, so let me give you an example where this is not true. Right, and then I'm going to call this y value A and this y value B. Okay, so in this case, the limit as x approaches c of f of x equals A, but the value of the function at x equals c, and we denote that as f of c, equals B. So because the value of the limit does not equal the value of the function, then this function is considered discontinuous. Okay, we're going to stop there, but then we will pick back up here tomorrow.